What is emergence?
You could try to say, well, if you knew all about particle physics and the theory of everything, then you could predict, a human being. But of course you can't. I suppose emergence is the question of how does this complexity that we see in the world emerge or appear from the simple underlying laws. In a sense, almost everything's emergent. I mean, clearly, we observe the universe at our particular scale, so sizes of things that we can see, and we're a particular size.
Right.
And so I suppose you could argue that everything that we understand and perceive as human beings is emergent, right? You could say that life is it's about information. It's really computing is what life is.
Holy moly.
So space-time is not fundamental. There's a deeper description, which is basically a network of qubits. So essentially it looks like a quantum computer, but absolutely not to say that we live in a simulation.
So there should be an energy associated with the wavelength that is a Planck length.
Yes. And you find out that that energy density makes a black hole.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck Nice. Chuck, baby.
Hey, Neil.
All right.
What's happening?
So you know what we got today?
Yeah.
We got an old favorite.
Yes, we do.
Oh, my gosh.
Someone who is, I will say, just as popular in the world of science as you.
No, he's way more popular.
No, I'm not going to go that far. I'm sorry. I know he's here.
There's objective evidence for what I just said.
Really?
Yes.
And what would that be?
I'll bring it up. Can I introduce the man first?
We're talking about him like he's not here.
I'm enjoying this.
Brian Cox. Yes. Welcome back, dude.
Thank you.
Yeah, you've been here long ago when we were on TV with National Geographic.
Yeah.
When StarTalk was...
I thought you still were. I've been misled.
Well, not on TV. We're still vibrantly podcasting. So you are Professor of Particle Physics at the University of Manchester.
Yeah.
And that's outside of London? Where is that specifically? Or is it in Manchester?
Manchester.
It's in Manchester.
The best way I can describe it is near Liverpool, if you're that. So
near Liverpool.
Yeah, it's roughly where the Beatles came from.
Yes. Yes. You've got very popular podcast, which I've been on once, maybe twice, The Infinite Monkey Cage.
Yeah.
Yes.
It just makes me laugh every time I hear it.
Yeah. I wonder whether it's a good title, actually, because it's not got science in it. So if you don't know what it is,
right,
you have no idea what it
And you know that it's addressing the probability of phenomena happening with an infinite number. Weren't people worried that you were actually caging monkeys?
We did have some complaints because it's a BBC show. A lot, the British people are very good at complaining in letter form,
right?
In green ink. Absolutely. You probably get some of that.
Green ink.
It's usually green ink,
and that means that that this letter is going to be exceedingly unpleasant.
Yes, and someone did complain about it being cruel. Although we pointed out that an infinite cage is roomy.
You think?
Arguably, the universe is an infinite monkey cage with monkeys in it.
That's pretty awesome.
And the monkeys don't complain about being contained in the universe.
Yeah, so they were tripping on the word cage there.
Yeah,
right.
Yeah, monkey in cage.
Right.
Infinite, they missed.
Yeah, they missed the infinite part. Right.
And Brian, you just coming off of a tour that put you in the Guinness Book of World Records.
Oh.
That is crazy fact. So what are the details of that?
The world record, which admittedly I'm not sure how much competition there is for the biggest science tour in the
biggest science tour in the world. Okay,
I got you.
It was it went on for quite some time. It went on for about 4 years in the end, and I think the number was something nearly 500,000 people came.
Okay,
which was a wonderful thing for people to come.
Now Taylor Swift would do that in 2 concerts.
Right.
Exactly.
Actually, she does that in the parking lot.
So if she decides to start speaking about cosmology and astronomy, she will beat that record. I feel I'm happy to lay down the gauntlet to her and say, go on then, break that record.
You bring on the challengers. Yeah. So it was counted as one tour because it was the same topic.
Yeah, it actually changed a lot. Because
but it had the same title.
It's another complaint we get actually on a BBC show. It's like, you scientists, you keep changing everything. We make new discoveries. So over that 4 years, it's been remarkable.
Because you had to stay current with the science.
Yeah.
And remind me the title of that? I actually saw that show.
That was Horizons.
Horizons, yes.
You saw an early version of it, I think.
Yeah. You've hosted multiple BBC shows.
Yeah.
With lofty titles, right? Like you'd taken on the whole universe, the solar system.
We've done a solar system type show 3 times.
Okay.
And did struggle with the title because the first one was called Wonders of the Solar System. It was initially, by the way, going to be called 7 Wonders of the Solar System.
Oh.
There's a very famous broadcaster called David Dimbleby. I don't know if you know him here. But he's an institution. And he had something else. I think it was called Seven Wonders of the World or something like that. It was on at the same time. And people thought that there might be some confusion. So they turned in to have this wonderful history show about the development of the British state or whatever it was, like, over 1,000 years. And they get me talking about planets. And so they just crossed the 7 out because I was the junior person.
Okay.
So they became Wonders of the Solar System. And then we did it again, about 10 years later and called it The Planets. And
Very
then
simple and direct.
And then we did it again. And then we thought, we've done Wonders of the Solar System, we've done the planet, so it got called Solar System. So we're starting to. So I don't think we can do another one just purely because
ran out of titles.
Yeah.
Okay.
Basically.
And you also had a cosmology show, right?
Yeah. So we've done
Wonders of the Universe,
cosmology.
I guess.
But it's interesting to me that usually the solar system shows do the best. And
is there
I don't
tangibility
know why,
to the objects that are in it?
Or also people know it already. They know
the moon,
about
the sun, the planet. And your first science project in elementary school is ball, styrofoam balls that you paint to mimic the planets. It's deep within us.
And someone said that to me. Even when you're little, you have those things over your bed
mobile.
when you're 2. And so maybe it's something about the planets, I think. And also it's easier to film. As you'll know, as a TV show, if you're talking about the volcanoes on Io, you can go to a volcano. Whereas if you're talking about a supermassive black hole, it's difficult to decide what to.
Kind of hard to send a film crew.
What to point the camera at.
So that's important. Sort of taproots to your visibility, your popularity, not only in the UK but worldwide. So now you're saying, all right, we got this Guinness Book of World Records record. Let's keep going.
Well, I
love this next topic. Emergence,
yeah.
Oh my gosh.
I love doing the live shows and I really enjoy writing them. And the Horizon show that you mentioned earlier had been written, 5 or 6 years ago because we start developing the graphics a long time in advance. So I'd had all these ideas for a very new show, partly or actually inspired by Kepler. So Johannes Kepler. You probably know, he wrote a very beautiful little book called The Six-Cornered Snowflake, which you can get today. It's still in print. You can get it on Kindle. It was about an experience he had in 1609. He writes it was New Year's Eve, 1609. So I think he's embellished it a bit. It's a beautiful story, though. He was walking across the Charles Bridge in Prague from the observatory to his patron's house for a party on New Year's Eve. And he realised he hadn't bought his patron a present. And then he noticed snowflakes landed on his arm. And he looked at them and he got interested in why they're all 6-cornered. His book's called The Six-Cornered Snowflake. So what is the origin of this symmetry of the snowflakes? And so he went to the party and he said to his benefactor, I have brought you the gift of almost nothing because I know how fond you are of nothing. But he said, in that gift of almost nothing, which is the snowflake, you can read the entire universe, which is a beautiful line. And so in this book, he speculates.
I got to tell you, that's the worst freaking gift I have
Kepler,
ever
he knew
heard.
this.
If you showed up at my house with a melted snowflake, I have bought you almost nothing. I'd be like, no, you bought me nothing.
Not almost nothing.
He knew this. It's a very funny book. So you get this insight into Kepler as a really witty kind of person. Yeah. So he obviously knew that.
Of course.
But the thing is, it's a very modern way of thinking because he's saying that the symmetry of the snowflake has some cause. He says there's a quote that's something like, I cannot believe that this symmetry, this 6-cornered nature can exist without reason because they're all 6-cornered. So there's a reason for it. And obviously we now know it's the water molecule.
Right.
We didn't know about molecules. Yeah. So he starts thinking about
beehives. Way late in there.
Really a 20th century discovery.
Yeah. Exactly.
So he talks about beehives and pomegranate seeds. But what's
beehive with the hexagon in the beehive. Yeah.
So he says, what's that? What's the reason for that? Which again is quite complicated. And we figured out in the 20th century different reasons. But for me, it's wonderful because you see this mind, this modern mind, asking a very modern question, which is what is the origin of this symmetry that we see.
Interesting.
And I think it's a really beautiful book. And at the end, by the way, he says, The translation I have is I'm knocking on the doors of chemistry. Now, I don't know whether that word was around at the time. That's the translation.
Alchemy was there for sure.
So he said, I'm knocking on the doors of chemistry, but I don't know enough, so I leave it to you, dear reader, to take the next step. It's an
humble.
Absolutely magnificent book.
Yeah.
So that it would be one of many examples of emergence.
Yeah.
Yeah, because I have a very limited list of what I know is emergent. One of them, and correct me if I'm wrong, you can study a bird all you want and know everything about it, but you would not know from that a bunch of birds will flock together.
And in syncopation, change direction all at once.
Exactly. You don't get that from studying the physiology of the bird.
Yeah.
And that's an example. That's a fine example, is it?
Yeah, emergence. I mean, even...
Well, you know what? Before we go any further, what is emergence?
Well, at an even deeper level, you could say consciousness is an emergent property. That's probably the most famous one that people discuss.
Yeah, well.
Because it's a property of some atoms and molecules in a particular configuration. We can discuss, some people don't think that, but that's the scientific view is that's what it is. But also there's this idea that it's not that there's a more fundamental description in a sense of a better description of this complex thing, as you said, like birds flocking. There are different levels of description that are appropriate in nature. So biology, you could try to say, well, if you knew all about particle physics and a theory of everything, then you could predict, a human being. But of course you can't. So in all science, there are different appropriate levels of description. Nuclear physics would be another one. You don't do nuclear physics, at least at the moment, by doing particle physics. So I suppose emergence is, to my mind, most simply the question of how does this complexity that we see in the world emerge or appear from the simple underlying laws.
And that is layered depending upon what you're observing in terms of biology or physics or the bird.
But in the end, would you say it's just all physics?
Well, no, I think the modern view is
I'm asking a physicist that.
Of course.
Yes and no. So yes, in the sense that the complexity that we see has an origin, of course, in the laws of nature that we understand. But scientifically speaking, the correct way of, the best way of being a biologist, trying to understand complex biological systems, is not to be a particle physicist. It's a completely different discipline. So
even if you are foundational to everything that's happening, it's pretty useless at the level of the biology.
Yeah, the standard model of particle physics, there's no point in trying to understand the brain by starting with a standard model of particle physics. You will get nowhere and probably never will.
Gotcha. The idea of emergence, where complex patterns arise from simple parts working together, is science in action. Ironically, the same principle is what's missing from much of today's science news. Between political spin and fragmented coverage, the bigger picture often gets lost and important discoveries get buried. Take this article, for example, about interstellar comet 3I Atlas. As you'll see, there's a large gap in who's covering this story. Gaps such as these are called blind spots, stories that have political undertones and are disproportionately covered by media sources on one side of the political spectrum. The contrast in coverage and who's reporting it further highlights the ideological divide between celebrating scientific prowess and fueling speculation. So, who can you trust? Well, that's why we're longtime fans of Ground News. Founded by a former NASA engineer who set out to bring clarity to complex stories, Ground News pulls reporting from tens of thousands of sources around the world, from peer-reviewed journals to international outlets, so you can actually see how the full story emerges. Ground News doesn't just filter the news, it gives you the context others skip. Which biases shape the coverage, how credible the source is, and who's funding it. We've partnered with Ground News for years because these tools matter more than ever. In a time where science is under pressure from politics and misinformation, you need something that keeps you ahead of the story. For just a small investment of $5 a month, you can further your understanding of the cosmos by heading to ground.news/StarTalk or scanning the QR code to get the same unlimited Vantage plan that we use. And with the holidays coming up, it makes a perfect gift for the curious people in your life. Even better, they'll get the same plan for the same $5 a month. You're welcome.
All right, so you built a whole public show, stage show on this one topic.
Well, it starts with Kepler. because one of the things I like doing with live shows is developing graphics and sort of spending time working with people. So it starts on the Charles Bridge with a snowstorm, and I tell that story.
But just to be clear, this is with a video wall.
Well, yeah, by video, that's the other cool thing, because I get to, in the big shows, I believe the video wall we're going to have is 100 feet wide by 50 feet high. So it's just the biggest LED wall you can fit in an arena. Mm-hmm. So, but it starts with that, but pretty quickly we go into the snowflake and then journey inwards initially. So the modern understanding of the snowflake with the water molecule, but why is the water molecule with that particular angle? 109 and
108 degrees. Yeah, 108 degrees.
108 degrees. So then you have the oxygen atom, the hydrogen atom.
There's the angle between the two hydrogen atoms coming off the oxygen.
Okay.
Which is the origin of the symmetry of the snowflake, ultimately. Right. And then you go to protons, and we go into the proton. I mean, my PhD was, broadly speaking, on the structure of the proton. I worked at a lab in Germany called DAISY, an accelerator called Hira.
DAISY has great graphical representations of physical phenomena.
Yeah.
It's DAISY collaboration.
A very famous lab, DAISY.
Yeah.
And so we were looking at the structure of the proton, really mapping the structure of the proton. So we're going to the proton and then into quarks. And quarks, so a proton made most simply as two up quarks and a down quark, which as far as we can see are point-like things. They may well not be point-like, they probably aren't, but we don't have a powerful enough microscope. So we just see this point. But then there are all sorts of other things in the proton, gluons and strange quarks and anti-strange quarks and things like that. So it gets complicated. So we zoom into that, and then we go a bit more speculative and zoom into maybe what are the building blocks of quarks? Is it superstrings? Is it string theory or something like that? So there's an element of a journey inwards and then a journey outwards again. So the show works, particularly in the second half, actually, physically with our intellectual journey. Because if you think about it, Kepler, you could say, I mean, you'll have comments on this, you could say that's the beginnings of modern science, around 1600.
Yeah, definitely. Well, this near simultaneous invention of the telescope and the microscope.
Yeah.
They came out within 10 years of each other. And we're often running in both directions. Once you have that,
Yeah, and it's, so, you're post-Copernicus, but Kepler's a contemporary of Galileo, pre-Newton. So in 400 years, we've gone from essentially the same view of the natural world that we had in ancient Egypt or Greece. I always think if you took an ancient Egyptian from 3000 BC and put them in Greece, about 0 AD or so, they wouldn't be too surprised. There wouldn't be much they didn't understand.
Right.
Whereas from 1600-ish, 1550, 1600, the whole modern world has developed in 400 years because we worked out how to do science, I would argue. I mean, some historians will be watching going, it's a bit more than that. But I think...
No, where science as it is now practiced took its taproots in that era. Yeah. I mean, where you have an hypothesis, you test it.
Right.
You don't just say something's true because it feels like it should be true.
Right. It has to be repeatable.
Even something so obvious as the sun goes around the earth. That's so obvious, why even test it? But you test it, right? And so this idea of testing, and we can't give short shrift to what's your institute in...
the Royal Society.
The Royal Society, yes, of London. Was that what they...
We just call it the Royal Society.
Excuse me.
Of course.
Okay. But that's
very British.
It is the Royal Society.
The Royal Society, as if there were another.
No, right.
So part of the show, although we're going inwards as far as we can go, outwards as far as we can go, talking about a lot of images from the James Webb Space Telescope, I think, because they're so spectacular. Vera Rubin Observatory now, so those latest images. And the problems they're raising, by the way, as an aside, about the early universe and the development of early galaxies and so on. But ultimately, is a thread, which is, this is a remarkable 400 years. And in the end, so the Voyager spacecraft actually starts to take became a character in this show. Because as this thing, which is its 50th anniversary is, 2027, isn't it?
Yeah, it was 1977 they were launched,
So it's kind of as our first emissary to the stars, I suppose, as Carl Sagan would say, as it begins to leave the stars. Yeah, that's how you'd say it, isn't it? So there's something, I think, quite current about how we learn to acquire reliable knowledge about the world, and how that has changed everybody's lives in a way that they never changed before. So you could go for 1,000 years or 2,000 years or 3,000 years. Nothing changes really. We don't discover antibiotics.
Right.
We don't discover medicine.
Right.
And then just 400 years from people like Kepler and Copernicus and Galileo, the modern world appears. And now we stand on this threshold, I think at almost a decision point. And it's our decision what we do with this power that we have. Do we go forward to the stars following Voyager? So is Voyager the first explorer and many will follow? Or does it become some kind of museum, with the golden record? Is it the last thing that we end up sending out of our solar system? So there's an element of that, I think, just reflecting on the position we are with so much.
You're going to be bumming some people out if you take that path.
Well, no, because I'm an optimist.
Oh, okay. Yeah.
But I think that we're at a stage now where the potential, the possibilities are so great, but the risks are also great. At the moment.
Part of the risk being raised or intensified is because of the technological advances and scientific advances that we have made.
Yeah.
They actually put us further at risk. So we are all at once the beneficiaries and the people harmed by our own advancements.
Yeah, I think we've talked about this before, haven't we? That it's our knowledge exceeds our wisdom. So we have power to do things like build nuclear weapons, for example, power to change the climate intentionally or unintentionally. And maybe we don't have the wisdom to control that power.
Yeah.
Bumming us out, dude.
Yeah,
but I'm an optimist. We've done well so far.
Right.
Yeah, we've had the power to
We've done well in
destroy
spite of
ourselves.
ourselves, really.
Yeah, we've had the power to destroy ourselves since
Several
the late
times,
1940s.
Yeah. I think, what do you feel about this? I mean, this is more philosophical, but for both of you, I think the amount of information that inundates the average person around the world now, thanks to, phones, places us in a position where there's more information available, but also more misinformation and abuse of information than ever before. So that, I think, raises the stakes in terms of us destroying ourselves.
Yeah, that's why I used the term reliable knowledge earlier. Okay. And I think that's one of the skills that all of us, our citizens, are going to have to learn, because we're awash with information, as you say. And now the trick is to try to find trusted sources. And it's not easy, clearly. And I don't necessarily blame, I don't blame individual citizens. To go back to Carl Sagan, one of my favorite books is The Demon Haunted World. And I love the first chapter where he tells the story of being in a taxi here in New York, actually, in a cab with a cab driver who says, "You're the astronomer on TV. What do you think about UFOs? What do you think about Atlantis? What do you think about and all of these things?" But Carl Sagan, I think, with great wisdom, said that he didn't think, "Oh God, this guy, he's talking to me about Atlantis." He thought, we have failed. That society has failed. This is a person with
put the blame back on himself.
Yeah, because this is a person who's curious and interested and fascinated by the mysteries.
Right.
But the real mysteries.
Right, the ones that are truly fascinating.
Yeah, hasn't had access to them, which is a failure of education.
So it's
society.
you guys' fault. It's you two. The two of you.
Well,
you guys have screwed us.
to an extent, yeah. Well, you know what he meant, though. I think it's really important that, because I meet people online, especially, but also just in everyday life, who are sort of, we've got this comet, when we will talk about the Atlas 3I comet that's going through at the moment, a fascinating thing that may be, what current estimates, maybe 7-8 billion years old. Has come from a distant star system.
Older than our solar system, which is only 4.5 billion.
Formed before the Earth formed. An unprecedented opportunity to observe material that's coming from a distant star system. And yet, you see people going, it's aliens. That's. I think this is what Carl Sagan meant. The reality of it, that this is something that formed before the Earth formed.
Right.
And is visiting our solar system and going back out into interstellar space, is more interesting than trying to say that it's some kind of completely useless. By the way, if it's an alien spaceship, it's not spending much time. It misses the Earth by, nearly 2 astronomical units.
Right.
It goes flying through the solar system, flying off again. It's been traveling for something like probably about 7 billion years or something like this. Can you imagine if anyone is sat in that
and you
thing
missed your exit.
going, oh, no.
7 billion years.
We'll go around again. We'll make a course correction and go around again. I'm sure it'll be fine. Not much will have changed in 7 billion years. I mean, it's in a hyperbolic orbit, right? It's not they don't even have the chance to come back.
Right.
But so that it's a good example, though.
Just to be clear, hyperbolic, there are like several categories of orbit. And, well, it's actually 3 orbits we can speak of.
And which are they?
One would be a circle.
All right.
But nothing is in a circle because there's always something going on. So most are ellipses.
Right.
And if you keep making the ellipse bigger and bigger, there's a point where it sort of opens up to the outside and you get a parabola.
Right.
But that's a very specific form of a hyperbola.
Right.
And so hyperbola is just, it comes in and goes out and it never moves back around.
You're not going to see it again.
Right.
I mean, actually, I suppose, thinking about it, probably it's in a bound orbit in the galaxy.
So
I don't think
it's orbiting something, but not the sun.
It's not the sun.
Right.
Yeah, it's hyperbolic to the sun. Right, not to something else. But give us more examples of emergence, just so we can get in the bathtub with you here.
The one that's always talked about that we mentioned is consciousness. I think, and it's becoming very topical because, of course, AI and the potential development of artificial general intelligence, we're not there yet, but AGI, raises this question of what intelligence, what the experience of being human is. And so there are different, I think there are 2 categories of emergence people speak of. Actually, Sean Carroll, if you had him on the show, he's got about 5 in a recent paper. He's got loads of category 2A and 3B or whatever.
Okay.
But broadly speaking, people think of weak and strong emergence.
Okay.
So weak emergence is what I think virtually every scientist would, certainly a physicist would say consciousness is, which is very complicated, the most complicated emergent phenomena we know of in the universe, I would say. But it comes from the underlying laws. So you could model it with a sufficiently powerful computer. You could imagine modeling how the human brain works. Right? I think most people would accept. There is also strong emergence, which is somehow the phenomena you see is not, you can't simulate it from the underlying laws. There's something else going on. Now, I would not subscribe to that. So I would say consciousness is interesting because it's weakly emergent. It emerges from this thing, the brain. How, we don't know.
What about the gas laws that we learn about in chemistry class that you can't derive from just looking at the movement of gas particles as individual? It's a macroscopic understanding of what's going on, highly accurate and very predictive, but I don't think you can derive them from just looking at how a molecule moves in a gas.
Well, you could in principle. That's the point. In principle, if you had a very if you
could model a bajillion particles,
if you could keep track of every single particle and then track them, then you would be able to then, in principle, determine.
Yeah, which actually goes back to what we talked about earlier. Though it'd be pointless. As you said, gases, you can understand them with pressure and volume and temperature.
Right, macroscopic objects, macroscopic entities. Yeah.
Why would you bother? Having a supercomputer track the motion of all and the momenta of all these things, it'd be a silly thing to do.
And does it matter if there's, I don't know how to say this properly, so I'll just ask. Does it matter if there are levels of emergence? Because when you say consciousness, animals are also conscious. There are dogs, they are clearly conscious. Chimpanzees, let's go down to monkeys. A capuchin helper monkey is definitely conscious, but is not conscious on what we would consider the level that we are. We don't know if it's pondering its existence and all that kind of stuff. Whales are definitely dolphins. So, but does it matter that there are levels of consciousness?
No. I mean, they would just be one of those remarkable properties of atoms. Was it again to quote Carl Sagan again? Didn't he say that a physicist is a hydrogen atom's way of learning about hydrogen atoms? Which is a great definition of a physicist.
That's a great quote. I never heard that.
I hadn't heard it at that level. I heard humans are a way for the universe to know itself.
That's also great. I've heard you say
that's a little higher up than hydrogen atoms.
Yeah, that's pretty cool though. That's another great quote.
That's another example. In cosmology, about 3 or 4 minutes after the Big Bang, you have 75% hydrogen, 25% helium, a bit of lithium, maybe. Not much else. Tiny bit of beryllium, I think. And that's it. And then you go, so there's also that story which I tell in the show of how you go from that, which we have a very good picture of, let's say 10 minutes after the Big Bang, how you then go to this 13.8 billion years later, which is stars and planets, yes, but us as well. It's a remarkable story, but it's understood in broad sweep. Yeah.
No, that is not true. We all know that the greatest story ever told is Jesus. Okay. Please stop.
Okay.
Well, he's an emergent thing too.
So true. I mean, so true.
Tell me about the wetness of water. What should we be thinking about that?
I'm sorry.
That's another good example of something that's appropriate to talk about liquids, and they're wet. And what does it mean to be wet? Yeah, but actually at the lower level, it's just a load of molecules. Right. Oxygen and hydrogen atoms which don't have the property wet. So again, it would be another example. So I mean, really, I mean, you can read by the literature.
You can't point to a molecule and say that's wet.
No.
But an ensemble of them, then you can measure it and see, okay, is it wet, is it not?
Interesting.
Okay.
Yeah, so, I mean, basically, I mean, in a sense, almost everything's emergent, right? That we, I mean, clearly, you know, we observe the universe at our particular scale, so sizes of things that we can see, and we're a particular size.
Right.
And so I suppose you could argue that everything that we understand and perceive as human beings is emergent, right?
But is it really? Because doesn't emergence have to have some special characteristics that otherwise would not be if you just did the same thing over and over again? For instance, the noise that happens after the cellular division of a sperm and an egg coming together, that starts a certain kind of noise that biologists don't know what, but they know that split, 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 split. And then that keeps going until there's a person, and then none of those people are the same. None of them. So, like, that to me is truly emergent, whereas when you talk about water, like, that is the connection of these, you know, this hydrogen, this oxygen. And I don't care. You just keep connecting them that way, and guess what? You're always going to get that. You're always going to get water. So is that truly emergent?
Oh.
You see what I'm saying?
Oh, so you're saying in some cases it's a precisely repeatable thing.
Yeah, exactly.
Whereas in sperm and egg, you get billions of different people.
Absolutely. And so the true nature of the emergence is in the uniqueness of those separating characteristics as opposed to something that is just repeatable.
Doesn't it come down to just how many variables you're working with?
Well, yeah, it's a really beautiful way of thinking about it. I hadn't thought about it in that way, but
I made Brian Cox
think
like differently. Hello.
Well,
okay. I'm joking. Go ahead.
And you could say, as Neil was just about to say, you could say, well, it's just the number of variables you have to keep track of.
Right.
I think you're right. There is something that feels very different between just wetness, as an example, you're a liquid.
Right.
That's an emergent behavior. But you're right that when you get to life, I mean, life is surely the most remarkable example of that. And actually, some of the work that we see, I was listening to some. There's a paper just been published. I've forgotten the name. It's from a Google research group about essentially seeing replicators, which is what we're talking about here, living things emerge. That behavior emerge just from random code. So it's a very beautiful paper. I wish I could remember the name. Maybe on the strap line here when we do this thing.
You mean in human written code?
Yeah. So you just do a very basic computing language, and essentially the concept of a Turing machine, which now I'd have to explain. But this idea that you can a computer is essentially just a tape with like characters on it, or you could have just ones and zeros on it, and something that goes along and can change those zeros into ones and ones into zeros. So it can read and write on the tape, and a few other properties. And Alan Turing back in the 1930s wrote a very famous paper which introduced the concept of a universal Turing machine. So all computers are equivalent to each other, essentially.
Oh.
And so, but there's some work been done on seeing how you can just start with no coding, really, just randomness and a couple of rules for computing, and you leave it, and over time you essentially get code written that can replicate. So you get coding sequences that can copy themselves, which is what you need.
There's an economic counterpart to this, okay?
Go ahead.
So you can go to the street corner and say, I need milk, and there's milk there. I need eggs. Eggs are there, and they'll sell you the eggs, okay? You didn't set up the shop. You didn't do anything. It's just there for you. And you can say, there must be some cosmic law that is serving my needs here and now. This must be some magic force. And then you realize it is very simple economic forces operating.
Right.
Okay? Buy it, sell it for more. Okay?
Right. The laws of supply, demand, and profit.
Yeah, exactly. And get a product someone wants. Okay? That's it. Everything else falls into place. So that would be not very many variables that lead to high complexity down the line.
Yeah. And the complexity emerges, to use that word, from really some very simple laws.
That's really cool, actually.
Think about it.
When you think about it.
Yeah, because I want to get rich.
Right.
And so I want to find something you want, and I'm going to sell it to you.
Right.
And I'm going to sell it at a profit so I can get rich.
Yeah.
And an entire economy unfolds out of that.
And that emerges out of this simple transaction that one person thinks, oh, it's there for me. And the other person is like, oh, I have to do that so that, I can profit from that.
Yeah, it depends how big your ego is to think the whole world is configured for you.
Yeah, well, listen, I'm in therapy for that.
For your ego.
And it's interesting because it raises, and this is not my field of expertise, but it raises questions about what life is.
Right.
Because you could say that life is it's about information. It's really computing is what life is.
Holy
some
moly.
level. So it's not really, what you're saying there really is biology, the nature, the physicality that we think of as life. We think of biological systems with DNA and all those things.
Right.
But you can argue that that's not the really interesting bit. Right. That's just the way that it's realized.
That's an expression. It's an expression of the true thing, which is the computing. Which, if that is the case, then we have stumbled into the creation of life that will replace us. Which is, if we ever get to artificial general intelligence, and what you're saying is an emergent property of computing, which is also an expression of life, then it's only a matter of time before that particular computing becomes a life form, which, of course, will outthink us, outlive us, out-everything us.
Terminator.
Well, yeah. And this is, again,
don't smile while you're agreeing with him on that.
No,
Can I see a sad face for once on that mug?
But one of the things I've been involved in, I'm involved at a research institute called the Francis Crick Institute in London, which is the biosciences. It's a wonderful place. It's a temple to curiosity. I love the place. There's a great Nobel Prize winner called Sir Paul Nurse, who's a good friend of mine, who won the Nobel Prize for cancer research, actually by looking at yeast cells. So it's a remarkable sort of fundamental study of life. But he really pioneered the building of this institute, or inspired it in his image, which is about
Francis
curiosity.
Crick co-discovered the DNA double helix.
That's why it's called the Crick Institute.
Yeah.
But we did some podcasts called A Question of Science, actually, which are around. And we just did them at the Crick Institute and with panels of experts. And it was wonderful for me because I just chaired it and asked the questions. Mm-hmm. And it was mainly audience questions, actually. But one of them was on AI. And there was an interesting split in the panel between the neuroscientists and the computer scientists.
Really?
So the neuroscientists really felt that, for example, large language models, which is what we have at the moment, were just symbol shuffling things, and the brain is fundamentally different to that. So we are not large language models.
I kind of feel that way about them as well.
I kind of feel that way too.
It's just rearranging statistical juxtapositions of words.
Right.
And
it's seeing all the probabilities.
I don't feel like it understands anything.
Yeah.
When I interact with a large language model, it's like there's this vacuous eyes staring back at me, and there's no soul behind it.
Yeah. Well, the argument what one of the panelists gave was that imagine that you're immortal, so time doesn't matter to you. Mm-hmm. But we could be in this room if we were immortal, and someone could start putting little symbols in under the door, and if we put the right symbol out, we'd get some food. Right. So we'd soon learn what the right symbol was, and then they put 2 through the door, and we'd do the same thing, and then 3. And ultimately, if we had a huge amount of time, kind of a near infinite amount of time, we'd end up having a conversation.
Right.
And we'd do it right. But at no point would we have any clue what was going on. We'd not have any understanding at all of what we were doing.
It's a transactional exchange of simple information that itself is not anything more than just
there's no understanding.
Symbols. There's no understanding.
That's one of the points of view that were expressed. But
was that the neuroscientist?
That was a neuroscientist who said that. I think it goes back to this philosopher called Searle. I think there's an argument he made a long time ago about symbol shuffling, Searle's argument. So it's similar to that. But one of the computer scientists said, no, that irrespective of what you think about that, that's what we are. So we don't know what we are. We don't know what consciousness is. So it could be that that's all we're doing. We're really, and it's true, I suppose, at the cellular level, at the level of a neuron.
Wow.
There's no understanding.
Don't tell me that. I don't want to think. I don't want to believe that.
Stuff.
Now that you mention it, there are acoustic stimuli coming from your mouth, entering my ear, hitting my brain, and now I process that, and some other response comes out, and maybe I'm not conscious of anything.
No, you're just like
I'm just
information processing and response machine.
Yeah,
it's very possible.
And I think that this debate is quite live, actually, amongst people, among many people who all know what they're talking about, and there are different views, which just shows you it's complex, a complex emergent phenomenon.
That makes sense, and that is why a lot of and these aren't like neuroscientists, computer scientists, but there's many in the AI world who feel like, given enough time, you just train the AI on everything. If you have enough time and enough computing power, they will definitely be truly thinking. They're like thinking the way we consider thinking.
Yeah.
Especially when you think of thinking in that way. Right. And it reminds me of a New Yorker comic, I think it was. There were two dolphins swimming, right, in this water park, and they're humans up walking on the walkway. And one dolphin says to the other, they open their mouths and noises go between them, but it's not clear they're actually communicating.
Yes, exactly. Right. Yes.
Yeah.
So I get that there's emergence in these complex systems, but what is this talk I hear of emergence from the standard model of particle physics? What's going on there? I thought that's a pretty straightforward grid of what exists and what should exist or how they interact.
If I understand the question right, so there are quite basic things about particles that are difficult to derive from the standard model. So the standard model is, here is the quarks and so up quark, down quark, electron.
It's an inventory.
So we have 12 matter particles, the Higgs boson, and then 3 forces that it describes.
It's an inventory.
Yeah. And then it tells us about the interactions, but it's got how particles interact with each other and through which forces do they interact.
Mm-hmm. Can I ask this? I don't care if I feel stupid or if I seem stupid. Why do you guys call them particles when it seems like everything that I read, once I go anywhere in depth, that it's more like a field of, I don't know. I can't. It's just some kind of amorphous field, but you call it a particle, which makes me think like a little piece of something that's kind of floating around, and it's a tiny little. But
they always are when we observe them.
So it's really about the observation.
Well, but you're right. So the standard model of particle physics is a quantum field theory. So you're right that the objects in the standard model are fields, but maybe it's historic nomenclature, but it's true that when you always see, we detect in a particle physics detector an electron.
Okay.
And it goes to a place in the detector.
And just to be clear, you detect the signature of an electron. You don't actually see the electron.
No, we don't see it, but we see it in the...
We see its path that it makes or other things that it has touched on its way through the system.
Track that it takes.
Track,
right. We have magnetic fields, and so the charged particles are deflected.
So are you seeing a disturbance in the field that shows up as this singular kind of identifier?
I think you have to say yes to that.
That's right.
Okay, yeah.
Yeah, I mean,
listen, I'm just trying to, as a layman, get my understanding like on point here, because sometimes when you guys talk, it makes, what happens is my physical association with the world kicks in, and I'm like, well, that can't be because it's not that. And so, that's why I'm asking this.
Yeah, and it's a good question about how are you to picture the existence of, solid this existence in terms of quantum fields. It's a rather abstract underlying description. So that's absolutely true.
Okay.
But you're right what you said, that they're just the particles are we'd say the excitations in the field. But
gotcha. All right. Very cool.
Can you start with a standard model and derive quantum field theory from it?
No, the standard model is a quantum field theory. So, and there are lots of what we call free parameters. So that ultimately things are put in by hand, and there are a lot of them.
Does that make
put in by hand,
standard model that much less satisfying to you? As
it's not complete. It's certainly not complete. I mean, for example, one of the most wonderful examples is that. So, how many matter particles are there in the standard model? So to make up you and me. So what's the minimal description of us? It's up quarks, down quarks, and electrons. That's it. And the up quarks and down quarks make the protons and neutrons, which sit inside the atomic nucleus, and the electrons go around to make the atoms, and that's it, right? 3 ingredients, basically. And there's another one called the electron neutrino, of which there are a lot streaming through our head now from the nuclear reactions in the sun. So the 4 things, that's it. Now, it turns out that there are also 2 copies of that set. So there's a thing called the charm quark and the strange quark, and the muon and a muon neutrino. So the muon, for example, it's a heavy electron. It's identical in every way except it's heavier. And then there's another set, the top quark and the bottom quark, and the tau neutrino. So 3 sets of these things. So the one that makes up everything, and then another 2. Why? We don't know. We don't know why there are 3 sets.
So
it's a good job
the particles of the universe are in triplicate, except we are familiar only with that lowest energy regime with electrons and
then we discovered the other ones, and we with some very straight little caveats. We know there are no more than 3.
Why not? How do you know there are no more than 3?
Because it was so the caveats are very weak. But so at the LEP collider at CERN, throughout the 1980s, 1990s, that machine was built in the 80s. It was run through the 90s. And
did you have a position at CERN for a while?
Yeah. So I worked on as we're building the LHC, I worked on some ideas for little detectors close to the beams and so on the Atlas experiment. Before that, there was an electron-positron collider there called LEP, which was in the same tunnel. And that was really a factory to make things called Z bosons, or Z bosons, as I call them. And they're to do with one of the forces of nature, the weak force. And by measuring exactly the what's called the lifetime, the behavior, let's say, of that particle, you can see how many things it can decay into. Because basically the general rule in particle physics is if you're very massive and you can fall to bits into lighter things, then you will. And the more chance there is, the more things you can fall to bits into, the more rapidly you fall to bits, right, basically. So you can measure how many particles this thing can decay into. And so with some caveats about other generations, as we call them, being extremely heavy, and you wouldn't see them, then you can see how many different kinds of particle this thing can fall into. So it's a very famous measurement. So we're sure that there are these 3 copies.
3 and only 3.
But that looks like the periodic table of the elements, right? Mendeleev, going back all those years ago. So the pattern that you can see that we all learn at school in the chemical elements, and there's an underlying reason for that, which is quantum mechanics and the way that everything works. But so there will be a reason why there are only those 3 families, but we don't know what it is.
Father, Son, and Holy Ghost.
It could be that.
That's the reason.
So there's a lot of that in the standard model. Right? There are a lot of things that we don't know. We don't fully understand the Higgs particle at all.
Okay.
We've detected this thing. It is
got the Nobel Prize given.
Yeah, and Higgs. It's a remarkable new property of nature, a new kind of thing in nature. But exactly how that works, whether and why. So we know that it gives masses to the fundamental particles, at least in the standard model. That's its job. But why it gives the masses to them? So why is the electron the mass that it is? In the standard model, you say because it interacts in this way with the Higgs field. And you go, why does it do that? And we say we don't know why it does that. So there are a lot of things in the standard model that you have to measure. And so it's not a theory of everything by any sense.
And how come it doesn't contain gravity?
Thing. Well, so now you're asking about a quantum theory of gravity.
Yeah.
And Einstein...
Up with it.
Einstein spent the last, 20 or 30 years of his life trying to find such a thing.
Don't cop out on us now, Brian.
So
Einstein tried this for a while,
we don't
guys.
Know.
No, we don't know.
I interviewed, it was an honor actually, I interviewed Roger Penrose a few weeks ago and chatted to him about these things. And Roger Penrose is one of the greats of the 20th and 21st century. He got the Nobel Prize for his work on black holes, for really a very famous paper from 1963, I think it was.
66?
Was it 60s?
Yeah, 60s, mid-60s, yeah.
Where he showed that with very minimal assumptions, a sufficiently massive star will collapse to form a space-time singularity, a black hole. So,
inevitably.
Yeah, inevitably. So Oppenheimer and Schneider did it just before the Second World War, but with some assumptions about symmetry. And you could say, well, nothing collapses in a perfectly symmetric way, so you wouldn't form a black hole. But Penrose removed those ideas. But he's a great relativist. He's a great, a real expert in general relativity. So he would not, I suppose the fashionable way to think about this is general relativity comes from quantum mechanics, but we don't know how. And there's some support for that from the study of black holes a bit. But there is another way of thinking that says, no, space-time is fundamental. Relativity is fundamental. I'm saying that because there's debate. I think most physicists would say quantum mechanics is the underlying theory, some kind of quantum description of nature.
It's on a roll.
And out of that emerges.
It's on a roll for how successful it has been in accounting for everything.
Yeah.
Right? I mean, so why doubt it at this point?
Yeah. So maybe we don't know enough to start. I think I'm not misrepresenting him. He would question whether you really need to have a quantum theory of gravity coming from quantum mechanics. I think he would question that. So the reason I'm saying that is to say it's an open question. We don't know. So
what about the fabric of space-time?
Ooh.
Is that emergent?
Well, so the recent work in the study of black holes, which is the tiny bit of research I still do. I had a PhD student and postdoc working on this. It's called emergent space-time.
What is that?
So it's the idea that space and time are not fundamental. So space-time is not fundamental. There's let's say a deeper description, which is basically a network of qubits, to do the shorthand version. So qubits, quantum bits. So essentially it looks like a quantum computer. Absolutely not to say that we live in a simulation. Right? No one's going.
He's a little defensive there. Have you noticed that? He sounded. I don't really mean that.
I don't know whether we live in a simulation. Nobody does, but I'm just saying it's not evidence for that.
Right.
But it's beginning to look like you can say, well, let's say a notion of distance can emerge from a network, an underlying network, which doesn't have the notion of distance or geometry in it. So you just described
subspace from Star Trek.
Did I?
Kind of.
Possibly.
Yeah, it's like this underlying substrate where the laws of physics aren't necessarily in play, which is why you can go faster than the speed of light.
Well, information goes faster.
Goes faster.
They communicate in subspace with witty repartee.
Exactly.
Even though they're
half a galaxy apart.
Right.
Yeah.
Right.
It's interesting. I was thinking about this in another context actually, because so there would be laws of physics, by the way. There'd be underlying laws.
Right.
And then our laws would emerge from them.
Please forgive my inelegant description.
We call them effective theories, right? So it's an effective theory,
right?
Which works in the regimes we observe things. But
effective theory.
But I was thinking about this, and I have no evidence for this at all. So I might cause lots of people to write in. But I think that causality, for example, cause and effect, which is what you're saying if things can go faster than light, then you can essentially build a time machine and go into the past. You can send messages back into the past if you can go faster than the speed of light, basically. My guess is that that's absolutely fundamental. And so you wouldn't, just because you can skip, if you could skip beneath relativity, so to a deeper picture of space-time, I still guess that causality will be there.
Will still be there.
I'm not aware of anyone who's proved that, or I'm not aware of anyone's opinion on it. It is my opinion.
Yeah.
I don't think I have any evidence for that other than Stephen Hawking.
How is that different from Stephen Hawking's time travel conjecture?
Yeah, the chronology protection conjecture.
Sorry.
So it's called a conjecture because he conjectured it.
It was conjecture.
And that was his conjecture, you're right. He said that whatever the underlying laws of physics are, they
have to prevent
time travel into the past, which is to say that causality.
Protecting causality.
Right, exactly.
But I think we're absolutely miles away. We're miles away. This might not be right, this idea of space-time emerging, although it's quite a popular research field. Mm-hmm. It is interesting because quantum mechanics can seem to violate the spirit of that. So you probably discussed before on the show quantum entanglement.
Yeah. Everybody wants to know about quantum entanglement.
Einstein called it spooky action at a distance, he called it, right? So he didn't like the idea that you can have these widely separated things that can appear to be correlated in such a way that something happens instantly. Now, we know, John Bell and others showed, and it's been experimentally tested, that information can't travel faster than the speed of light.
Right.
But still, the idea that some kind of, call it configuration, that the quantum state can change instantly, seems to violate that somehow, doesn't it? So this is, again,
I heard from
research.
the other Brian.
Brian Green.
So I was having lunch with him, and he said something that just blew my mind. What might be fundamental in space-time is this sea of entangled virtual particles, where the particles are entangled via what are essentially wormholes.
Yeah.
Because a wormhole has instantaneous contact from one side to the other, and the wormholes then are the stitching of the fabric of space-time.
It's called ER equals EPR, which is Einstein-Rosen equals Einstein-Podolsky-Rosen. So EPR is the spooky action at a distance paper, and ER is Einstein-Rosen, which is 1935, I think, where they showed that the Schwarzschild metric, the eternal Schwarzschild metric, which is the description of a non-spinning black hole, which was discovered very early in relativity, has in it, if you extend it as far as you can, a wormhole geometry. So that was Einstein and Rosen. So it's called, I think Leonard Susskind coined the term ER equals EPR.
So what does that mean to you as a thinker in this space? Can wormholes be the fabric of anything?
Yeah, it's part of the answer. One of the answers for how information might get out of a black hole. So it's what it's called the black hole information paradox.
That's very cool. Go ahead.
Yeah. Well, one of the pictures people have for that very hand wavy picture is that wormholes somehow connect the interior of the black hole to the external universe.
But all the other virtual particles that fill the vacuum of space, those are particle pairs that come in and out of existence.
Yeah, they're entangled.
Why wouldn't they be? They're entangled. Why wouldn't that also be in this wormhole discussion?
Yeah. Yeah, exactly.
Okay.
So that's it. So it seems there's some sense of a link. The reason it came in the black hole context is people did very complicated mathematical calculations about what happens to the Hawking radiation. So this is the radiation that is emitted from a black hole. And it's really, one way to think about it is it's the event horizon of a black hole is disrupting these particles that you talked about, these entangled particles that are really the structure of the vacuum of space, right? And it kind of disrupts them. And so people were calculating how that radiation, which is entangled with the black hole, how everything behaves as the black hole shrinks. Because if you think about it, this black hole is glowing, it has a temperature, losing energy
through Hawking radiation.
Through the Hawking radiation. So not at the moment, because they're much colder than the cosmic microwave background. So they're cold things at the moment. But eventually in the universe, there'll be hot things, and they'll shrink.
It'll be hotter than the background.
Yeah.
So there'll be net flow of energy is out.
Yeah. Hot is, I mean, we're talking about 0.0000 whatever Kelvin. But eventually they'll shrink. they're entangled with the Hawking radiation because of what you said, because of these pairs that are coming out of the vacuum. And so you get to a point where you get a crisis, really, where the entanglement can't be supported. It's one way of thinking about one of the problems with the black hole information paradox. So it's all to do with entanglement and what happens. And so from that research, some calculations were done, which are just mathematical, that say that ultimately the Hawking radiation ends up essentially entangled with itself again, right? It's one way to think about it, because so you don't lose information, but those calculations can be pictured with hand waving as representing wormholes, some sort of wormholes. They're not the Einstein-Rosen wormholes, actually. So it gets very complicated, and people aren't clear on the interpretation. But that's where the modern resurgence in this idea has come from. I think it's coming from these really very technical calculations about black holes and how information behaves in the presence of black holes. And wormhole-like structures appear to be one interpretation of what's happening. But I'm choosing my words carefully because it really isn't fully fleshed out by a long way. Yeah. It's interesting, isn't it?
But it is really fascinating to think about. Like,
this
is how it's like an information tunnel just for that, for the purposes of getting it out.
Yeah. So, and then you go, why? And even, you see the language. It's like for the purposes of why is it that information is conserved? Right. That looks quite basic. So it looks like another of these basic ideas. Information is not destroyed.
Right.
It becomes massively scrambled, so you can't in any conceivable future read the stuff. But it's the example that's often given is if you burn, but it's the iPad. Let's say you set fire to the iPad, you might say, well, surely I destroy the memory. But the idea is that you don't, if you could measure everything that came off somehow, all the photons and everything, the whole thing, then in there scrambled up, you could reconstruct.
Would be the iPad, even though you set it on fire and all those atoms, and every particle that was in there. If you could get them all together, you would be able to say, "Oh, that was the iPad."
Yeah, and you'd have your photos in there, whatever it is. You could, in very principle, but really in principle, not practice, reconstruct. So you don't destroy information.
You don't destroy information.
It's also determinism. It's called unitary evolution in our language, right?
Really?
You don't destroy information.
Gotcha. So that energy and information, conservation of energy, conservation of information. Can we think about them like that, or is it not? Is that a wrong way to think about it?
It's less about information, more about entropy, right? I mean, entropy you can move from one place to another, and then you can measure that or think about it as an entity. Whereas,
I get that.
A point we were raising before, obviously if I send a molecule that has structure, a DNA molecule, into a black hole, and it gets ripped apart, and then it comes out as separate atoms, I lost all that DNA information. However, that DNA became DNA at the expense of the sun or whatever other input of energy.
The energy that went into it.
That's correct.
Gotcha.
Right. So you draw a sphere around all the action.
Somebody give me some weed. This is awesome. I should be high right now, man.
So then you could talk about sort of entropy moving,
right?
Without having to inventory the shape of the DNA molecule.
Right, because the DNA molecule is a result of the energy.
It was taking energy from another system.
From another source that put it in that made
Correct, yeah.
Oh, wow.
Yeah.
Okay. This is great.
You're right though. I mean, it's so fascinating this work on black holes, black hole information paradox, emergent space-time.
Yes.
But it's such a early stage that I don't think there are popular articles that really, the language isn't there yet. It's just mathematically difficult.
Yeah. Wow, man.
So we're doubling up on this and adding a whole segment of Cosmic Queries, which is a branch of what we do here. It's beyond just conversations. People get to ask questions. And we tell them who the guest is going to be, and they direct questions to that guest. You have been duly outed on our pages, and you have a whole fan base out there, and they're eager and dying to hear from you. And we have some professional overlap, but in the questions that'll come in, it's not likely that I will ever need to jump in. And I look forward to basking in your brilliance in the face of these questions. But I'm going to lead off, if I may. Do I have to fork up $5 for the Patreon?
I would like to have it.
Okay, because it's Patreon supporters who,
which is a good
they're
opportunity.
the only ones who get to ask questions.
Absolutely.
So this actually came in by a Patreon supporter. So actually, I'm channeling it.
All right.
Quarks. You've never had an isolated quark.
No.
Okay.
Oh, I remember this question.
I know.
Yes.
I know, and I couldn't answer it.
Yes.
I said, I need one of the Bryans here.
Right.
And we got one in
We got
flesh.
one now.
Okay.
Excellent.
Here it goes. You ready? So as you pull two quarks apart, you're actually putting energy into the system by doing so, like pulling a rubber band apart. And at the point where the quark connection breaks, there's enough energy you just put in so whole new quarks are created. So now you have two pairs of quarks.
Yeah.
I might be simplifying it, but that's the idea.
Yeah, basically. We call it hadronization.
Hadronization.
In particle physics.
Okay.
Yeah. And we have models of it.
Okay, gotcha. So now watch. I now have a quark pair falling into a black hole. It's nearing the singularity. Tidal forces stretch it, putting energy into it. It splits, makes two pairs of quarks, and they keep falling in. Will this create a quark catastrophe? Because the tidal force will continue to split the quarks and make a new pair of quarks. Will the singularity be overridden with quarks that were created from the tidal separation and the formation of brand new quarks in the energy that was invested in it? Am I taking energy out of the black hole by making quarks with it? What's going on there? And I'd rather think of it as I want to think of it as a quark catastrophe because that's way more fun.
I mean, you're not taking energy out of the black hole because all this is happening inside the horizon. For a big black hole, anyway, I mean, I suppose you could say for a micro black hole
where the separation is on the same scale of that.
But
okay, but why don't I just make a bajillion quarks as it falls towards the?
I've never thought of it before. It's a beautiful picture.
Yes,
because clearly you'll do that. You rip matter apart. That's the way it's usually said. Mm-hmm. So people just say matter, everything gets ripped apart. Even the protons and neutrons and even the quarks get ripped apart when you go to the singularity.
But to rip apart a quark has consequences.
Yeah, and we don't know what the singularity is. I mean, other than it looks like a moment in time. It looks like the end of time, which we've discussed before, I think, which is also a difficult thing to think about. So there's a finite amount of time in there for the quarks themselves when they're inside the.
That's a way out of that.
But
wait, just to be clear, was that what Penrose said? Because as you cross the event horizon, what was previously in front of you in space is now in front of you in time.
Yeah.
Because we had Jan 11 here. She's our resident, up the street cosmologist. Yeah. So the time in front of you is finite. So it can't keep splitting quarks forever and creating.
No, you don't have forever. I mean, even off the top of my head, even the big black hole, like the M87 black hole, which is the one we have a photograph of.
Yeah, the one that had all the ones that made the news.
6 billion solar masses or something like that thing.
Yeah.
And in there, I think you have about a day. It's about 24 hours or so if you cross the horizon before you go to the end of time. Wow. It's roughly speaking a day, give or take a factor of 2. I can't remember exactly what it is, but it's something like that. So
that's freaking crazy.
So there's a finite amount.
So trippy.
You have a day left before time ends.
Yeah, and you wouldn't notice.
And you wouldn't know it.
No, you wouldn't notice.
Oh
we could be. I mean, it's one of the fundamental properties.
Wait,
of
why
general
can't I
relativity.
notice it?
Well, you wouldn't notice until the tidal forces became important.
Right.
Which is what you're referring to.
Then it gets ripped apart.
Right.
Yeah, so when you cross the horizon, this room, we could be falling across the horizon in Einstein's picture, purely in Einstein's picture. We could be falling across the horizon of a supermassive black hole, would not notice.
Right.
So from our perspective, everything's normal. Ultimately, you'd feel the tidal forces. But
as you get closer to the singularity.
I think it's within the last few seconds for these, if I remember rightly, for the very big black holes. And then you feel it. And then it's tidal forces, but you wouldn't have time to react, really. You just go, that's a bit.
Right, but so you're not going to make an infinite number of quarks.
No, you won't make an infinite number of quarks.
Because time stops it.
Right.
I think
you
that's
actually get to
probably
the end of time.
Having never thought about it, that's probably the answer.
Wow, that's so
energy is conserved as well, so you couldn't make an infinite number of massive
Maybe
things,
it could evaporate the black hole.
So you'd be
It could turn the whole black hole into quarks.
Well,
because it's pulling energy out of the.
Well, no, the mass of the black hole will stay the same. So that process of hadronization.
I get that the mass will stay the same, but that mass energy budget is slowly getting converted into quarks because the quarks will keep making new quarks because you keep trying to rip them apart with your tidal forces.
So
you're saying that the quarks are a drain on the electric bill.
So you're saying that space-time would unwarp because the energy
will be completely converted
into matter.
And you have one giant quark. The quark catastrophe.
That's not what happens, isn't it? But it's
how do you know that's not what happens?
It's a brilliant question because we see black holes.
Oh, okay. Well,
so
that's the answer.
There you go.
Oh, yeah. No, okay, that's it. I can't argue.
You cannot.
So they haven't. The geometry is not unfolding
to them. So then you're left answering why it did not happen.
Right.
That's what
and I think I suspect the answer is because of the finite time you have in there.
That's so cool.
So.
All right.
But there's some weed for you now. You want some?
Yeah, please.
It's also important to say that we don't know what the singularity is.
Right.
So we really.
And we can't calculate with it or anything.
Yeah, because you can't get inside a black hole to see what it is.
Well, the theory.
Well, thank you for that. That was from an earlier Patreon question.
It's a great question.
I don't know. I don't know.
I'd never thought of it.
Yeah, that came from one of our listeners.
One of our people.
One of our Patreon patrons. Which, by the way, you can be one for $5 a month as the entry, just to let you know.
It deserves more than it deserves the money back for that question. It's a great question. Refund.
Stump the expert.
You get a month free, buddy. That question was so great. That's funny.
Yeah.
Okay. So Raul starts us off. Raul. And he says, hello, Lord Nice, Dr. Tyson, Professor Cox. I'm Raul, a new Patreon member from a couple streets north of where you guys are right now on Central Park. I wanted to know if there was any discourse on whether dark matter and dark energy, affectionately dubbed as Fred and Wilma by Dr. Tyson, are emergent phenomena resulting from the curved manifold of space-time. In the case of dark energy, could it be that geometry of space allows for peaks and troughs for the accelerated expansion of space, and we just happen to be observing the expansion phase? Thanks for all that you continue to do for science.
I have to explain Fred and Wilma here before we begin.
Okay.
So I've had taken issue with the terms we have invoked to describe dark energy and dark matter because it implies that it's energy and matter. And I said, what we know is that it's dark gravity. That is what it is. We don't know if it's matter. Maybe it is, probably it is, but we don't know.
Yeah.
And dark energy, is it energy? We don't know.
Yeah.
So I said we should just call them Fred and Wilma.
Yeah.
Okay? And that way there's no bias associated with the label.
Yeah, and that's how I was going to answer the question. Is in that there are different. So dark energy. So as you said, observationally, and we already mentioned Brian Schmitz, who was one of the people who discovered that the universe is accelerating. There is in Einstein's theory of general relativity a thing called the cosmological constant, which you can just put in, and it does that job. But whether that's what we're seeing is a good question, and we don't know the answer. So it could be that you're seeing some kind of quantum field, which we talked about earlier. So, for example, inflation, which is the idea that before the universe was hot and dense, so before what we call the hot Big Bang, then space was stretching extremely fast, driven by something which we call the inflaton field, which is one of these quantum fields we talk about. And then that field changes and decays away. That's the end of inflation and the heating up of the universe, which we call the hot Big Bang. So it could be that dark energy is something like that. So it's some kind of quantum field that's doing it. That may mean that it changes, and it could change over time. And indeed,
so it could go away.
So it could go away. And I think that there's in the current data, which is associated with the early universe, there's a tension in between the things we measure, like the Hubble parameter and things like that, from the early universe, from the cosmic microwave background radiation, and the measurements from the later universe, which is from seeing supernova explosions and so on, seeing the expansion of the universe that way. And there are some sort of almost, probably not hand-wavy, but preliminary ideas that you could be seeing that something was present in the early universe that is not present now, or vice versa. So something's changed. So it is true that inflation would be an example, if it's correct, of one of those quantum fields which then changes and goes away. And that's associated with what we used to call the origin of the universe, right? Wow. So it could be that dark energy is something like that. And also, actually, to add to that mystery, there's the Higgs field. So the Higgs field is what's called a scalar field, which is technical jargon, but it's of the same type of thing that we think the inflaton field is, and possibly the dark energy is. So but the Higgs field doesn't appear to cause the universe. Well, it does not cause the universe to accelerate in its expansion, or at least not in the way that we would expect. We'd expect it to blow the universe apart, and it doesn't. So there's something in there. Many of my colleagues think that associated with these things called scalar fields and the way they interact.
Is that something that's going to pop out of a future run of the Large Hadron Collider?
No, I don't think so. I think it's more theoretical advances that but precision measurements of the way the universe is expanding and has expanded, the expansion history of the universe. Because these things are all encoded in there somewhere. So I think it's that. So the answer is to the question is we don't have a model. We don't have we have lots of models of what dark energy might be, but none of them are agreed upon or more convincing than the other. Right? We don't have enough measurement, I think, precision measurement. So it's a very good question. And the same with dark matter, we do have more evidence that it's some kind of particle. And some of that comes from, so I mentioned it, the cosmic microwave background. I should say what it is. It's the afterglow of the Big Bang. It's often described, the oldest light in the universe. So they're photons emitted about 380,000 years after the Big Bang, which we can detect. So it is a measurement. There's a satellite called Planck that made the highest resolution pictures of this that we have at the moment. And so in there, you can model the way that image looks. It's actually sound waves moving through the universe before 380,000 years after the Big Bang. So what you're seeing is sound waves in the plasma that was the early universe. And we can
We're seeing an imprint of those sound waves at that time.
So we're seeing the imprint when the light got released, when the plasma went away. Yeah. Essentially what happens is...
So there was an actual bang?
No, I mean, that's what Fred Hoyle used the term, because he thought he was so stupid. It's not a bang.
Right.
As I described it, it's the end of inflation. So whatever. Exactly. We don't... But so these are sound waves. Wow. But we have a very good measurement. We have that photograph, which shows us there is the information about the sound waves. And that allows us to model what the plasma is and what's in it. And the dark matter is a very important component of modeling the way those sound waves behave. So it's often presented as something that people invented because they don't understand how galaxies rotate or interact or something like that.
That's a real thing.
But you can see it in many different ways. So it is true that the way that our theories of galaxy formation require it, there's a thing called the cosmic web that you've probably talked about before. But there's also independent measurements from the sound waves in the plasma of the young universe, and that requires them. And you can do, actually my postdoc actually did it for, it's one of the things that's in the show, not that I'm always plugging these tickets for the new show, but one of the things I do in the show is my postdoc, Ross, is great, developed a real-time calculation tool of the way the sound waves work in the plasma. And what's cool about it is you can sit there with an iPad on stage and you can just go, I'll change the recipe. I'll make the dark matter go to like 15% rather than 25% or whatever it is. Play around with those things. And when you do that, the data goes completely, it doesn't match the data. The prediction drifts completely from what we see in the data. So it's highly sensitive.
Wow.
It's a beautiful demonstration of how accurate astrophysics is now, how accurate cosmology is. So I would be very surprised if dark matter isn't some kind of particle
itself.
because there's multiple different independent observations that suggest it is. Dark energy, we don't have precision, the precision, I think, to discriminate between the models.
Cool, man.
And you thought I'd give a long answer.
Well, it's a very good question. All right, I can see that we have to speed up. I'll speed up.
I'm good for long answers from either one of you. I don't care.
Keep it going.
Donita Bukait or Bushite, one or the other. And she says, hey, Neil, Brian, Chuck, Donita from Southern Utah. Help! I need visuals. How does the curvature of space-time cause tides? I've read explanations, but since I think in pictures, I need some visual support on this.
So imagine the Earth, and if you try to explain the tides in the ocean by just having a static picture of the Earth and the Moon just standing
as
still,
is drawn in textbooks.
As is drawn in textbooks, then it's hard to figure out what's happening because, as Richard Feynman said in the Feynman lectures, if everything's just standing still, if the Moon and the Earth are just standing still, they'll just be pulled towards each other and squash into
two
each
magnets, like when you set them down on a table and they come together.
So, of course, the reason they don't do that is because they're in orbit around their common center of mass. So they're orbiting. And actually, you need to know that the Earth is actually orbiting around the center of mass of the Earth-Moon system, as is the Moon, in order to fully explain the tides. And so you get a good explanation. So there are centrifugal forces at work as well, because you're in this frame of reference that's spinning around and so on. So it's actually relatively easy to describe, but not as easy as it's presented on television usually.
Gotcha. So, and you got into an argument with the producer on this.
Yeah, so I said I can't do it without talking about the fact that when there's a centrifugal forces. It's basically because the centrifugal force exceeds the gravitational pull of the Moon on one side of the Earth and is smaller than it on the other one. It's that kind of effect, but it's beautifully described in the Feynman lectures, which are freely available online.
Is that right?
You can
online
get them.
now.
I think they're free.
Cool. I spent real money on mine.
Well, the books
I have
you have to get.
I have hardcover. I got them in the. When did I get them?
They're beautiful.
In 1981, I bought them.
Yeah.
Okay.
But it's in there. You can download. I think they're freely available now.
And there's 3 volumes, right? So classical mechanics, E&M, and then quantum.
Yeah, it's in volume 1.
Very nice.
It's really lovely explanation of it.
So there you have it, Donita. And also you can check out the explainer that Neil did on tidal bulges. That might help you too. It's really
I forgot
good.
about that.
That's correct.
You remember all of our explainers.
Why do you think I do this job?
Okay. All right.
I get a free education. All right, here we go. This is Alyssa Feldhaus. Sorry. Alyssa from Tucson, Arizona here. Question for Dr. Tyson and Dr. Cox. Do you think the concept of a particle will still be meaningful once we fully unify quantum mechanics and gravity, or will it vanish like the idea of a phlogiston did in chemistry?
No, it'll be meaningful. We've been talking about emergence a lot. So different levels of description. So yes, it may well be that there's a theory of nature that we have it, right? It's quantum field theory, that just quantum fields, and there may be a deeper level in terms of qubits or whatever those things are, Planck scale things. But there will always be a level of description that where particles are the right thing. When you think about an old-fashioned TV, a cathode ray tube, where you have a beam of electrons, and the beam of electrons goes through a magnetic field, and it jiggles the beam around, and you get the picture on the TV. There's never going to be a better description of that than a beam of electrons.
Right.
So maybe a deeper part of that question is, if we come to understand that everything is strings, then we don't need the language of particles. Once again, is it just a convenience?
You will need the language of particles to explain things that are happening in this room, these energies and temperatures. Because
that's how it manifests.
Yeah, it's just pointless. You wouldn't talk about these phenomena that only become important for your description of the world at energies that, trillions of a second after the Big Bang.
Yeah. Okay.
I mean, just to say quarks, right? Quarks are not that. You don't need those to describe nuclear physics. You want protons and neutrons. Right. Those are the things that you need. And so the quarks are hidden inside. You don't feel them. You don't perceive them. That's why we didn't discover them until 1968. I think.
It was pretty late. You were on our way to the moon, and we don't yet know that quarks are real. Yeah.
That's wild.
Yeah.
That is wild.
All right.
We're stupid. Okay. This is David Villasmil, who says...
Is that the best you can do with these people's names?
Hey, listen.
Chuck.
That's his name now.
Villasmil.
Yeah.
Villasmil.
Villasmil. Okay. Yeah.
That's his
You
name.
made him French.
That's what I'm saying. That's his name now. Villasmil. So this is, anyway, he says, hello, Dr. Cox. I've been a fan forever.
All right.
Dr. Tyson and Dr. Tice, you guys are awesome. Anyway, how do particles know it's time to decay?
Love that question.
That's a great question.
Yeah.
Sorry about your name, David, because since you asked such a great question.
So what's the best way of describing that? Is time. So they have a lifetime, which is, as I said before, is to do with, can you decay into something lighter? So there might be a reason you can't, right? Because things are like electric charge, for example. Electric charge is conserved. So you can't take a positive charge thing and have it decay into a lighter, negatively charged thing, because you'd be inventing. You can't destroy and create electric charge. You have to do it in pairs. It's conserved. A very important example is the neutron and the proton. So the neutron is a bit heavier than the proton. So the neutron can change into a proton.
And does.
In about 10 minutes.
Yeah.
Oh, so,
I thought it was even quicker though, like 6 minutes.
Is it or 8 minutes?
Yeah. It's like you can count it out and watch
it happen.
Yeah.
If it's sat on its own, it'll do that, and to conserve charge, there'll be a positive thing will go as well, and so basically it can do it. So, and the lifetime is really proportional to the difference in mass between the neutron and the proton, which is very tiny. So if it was really big, if it was much heavier, it'd decay quicker. So you've got there's the mass difference, and then there's the number of things you can decay into, the number of ways you can do it.
Yeah, but that's just a statistical average. The decay time. That's the half-life.
Yes, half-life.
Okay,
yeah.
so we fill out the time with some of them are decaying sooner or longer. So it's not just as simple as you described, where how much difference is there in the energy of the mass of what it is and what it can be, because there's a variation in there. And I interpret that question as, how do you get that variation?
Oh well, that's quantum mechanics. So it's statistical.
Don't say that's the answer.
Well, but you're right. It's a very deep question.
Yeah,
it's like, and that bothered immensely the early founders of quantum mechanics. So people like Rutherford and those people who Niels Bohr and all those people, and Einstein, it bothered a lot. God does not play dice with the universe. That's essentially what you're saying. You're saying, why does God play dice, as Einstein put it? So the reason...
He was late on the mortgage for the universe.
Yeah.
So he plays dice to get some extra cash on the side.
Papa got to make this money.
So I think it was...
Papa got to make this money, baby. Come on.
Wait, but Brian, I realized just while you were speaking that you did answer her question precisely, because she said, because why do some take longer than others?
Yeah.
And the difference in how many options it has coming out the other side.
And the mass difference.
So that'll say why one will decay in 5 minutes or 10 hours. You can get that.
Yeah.
Okay. Given that, what is going on at the instant that it decays?
It's another
because
question.
Does that give me insight into why some will decay sooner and some will decay later, so that it averages out to that half-life?
So what's going on? So you can, it's called the weak nuclear force that's changing these things. So that's part of the standard model. So what actually happens when a neutron turns into a proton? So a down quark turns into an up quark. So what happens is the down quark, you can think of it as emitting a particle, a force carrying particle comes off. It's a W minus, which then goes to an electron and a thing called an anti-electron neutrino, actually. But it goes, so the W minus goes off, and then you get a down quark, which is a charge plus 2/3.
Okay.
So you get a minus 1/3 quark going to a plus 2/3 quark, and then you get an electron that comes off. So all the charges are conserved.
Gotcha.
So you haven't invented electric charge.
You have right.
And
So
also
the
when
sum of all the charges at the end is the same as the
we got
sum
it.
of
And when we think of a neutron decaying to a proton, all that's the engine process going on. That's the gearing that's happening that you just described.
So it's the same kind of picture as why does an electron bounce off another electron? So we'd say, well, because they've got negative charge and negative charges repel. But the particle physics picture of that is that a photon is exchanged between the electrons. So in this case, it's not the electromagnetic force, it's called the weak nuclear force. Basically, the down quark is changing into an up quark with ultimately the emission of an electron and a neutrino, and the W minus is the particle.
And in the end, when that happens, it's statistical. Wow. We got to deal with that. Are we hiding our awareness of objective reality by dusting it into the bin of probability?
No, it's not the same. That randomness is not the same as the randomness because we don't know everything. So in terms of a gas, let's say, there are things are jiggling around. We don't keep track. We spoke about it earlier. We don't keep track of the billions of molecules in the gas. So there's some statistics comes in because we're averaging over a load. The quantum mechanics is not like that. As far as we can tell, the statistical nature of it is inherently, it's built into the theory, it's built into nature. That bothered everybody.
So Einstein was just wrong.
Yes. Yeah.
Well, Einstein didn't like it. It is true that how to interpret that, then it's a whole other episode, right? So you've probably talked to people about the many worlds interpretation of quantum mechanics. Now, that's this thing. That's all in this. How do you interpret those statistical predictions
without
the collapse of the wave function,
without invoking a statistical description?
Yeah, I mean, so it seems that it's a fundamental part of the theory.
My favorite part of particle decay?
What's that?
If you accelerate them,
right,
then they take longer to decay.
That makes sense.
Because Einstein's special theory of relativity.
That's
you're so badass.
Going closer to the speed of light, so time literally is slowing down.
And so it takes longer to decay.
Yeah.
That's a beautiful thing.
That's very cool, man.
Yeah.
Wow. All right.
Time for a few more.
All right, here we go. This is John. He says, hello, Lord Nice and Dr. Tyson, Dr. Cox. John from Arkansas here. You've both explained what a Planck length is and how we will likely never get more accurate measurements beyond this supposed limit. I am wondering if light can have a wavelength that small and if energy would be measurable, or could that be another infinity we need new physics to explain, much like the singularity in a black hole? P.S. Love the show, and Chuck, I figured I'd mention you first for a change. Anyway,
there is an answer to this.
I love this question.
Yeah,
I would not have been able to answer this question.
The answer is that so the smaller you make the wavelength of a photon, the higher the energy is.
Yes.
So
there should be an energy associated with the wavelength that is a Planck length.
Yes. And you find out that that's that energy density makes a black hole. So I think
oh my effing God!
So if you think about it, the more you try to probe smaller, and then the black hole would. I think Len Susskind calls it the UV-IR connection. I think that's what he calls it. So the upshot is that if you try to put more and more energy into a smaller and smaller space to see smaller things, the size of the black hole you make increases. It grows.
That's wild.
So the more you try to see smaller things, the less you can see the small things. Right. Because the black hole gets
the universe
bigger.
is diabolical.
Yes.
Yeah. So it stops you. So you can't probe it.
So black holes are in the cosmological witness protection program.
Yeah.
You can't get in there.
You just can't. No matter what you do, you're not going to. That's amazing. What a great question, bro. That was awesome.
Okay.
All right.
And just remind us briefly about a Planck length. Just put that on the map here.
So you can construct units, fundamental units from things from specifically the speed of light, the strength of gravity, and Planck's constant. So if you take those things and put them together, so you get meters out, you'll get the Planck length. So it's Planck who figured out that it would be good to make units of measurement out of things on which everyone would agree. If you meet an alien, for example, then there's no point in talking about a meter, because what is it? It's the length of your arm or something like that.
Oh, no, it's 1/10,000,000th the length of a quarter of the Earth from the North Pole to the equator through the Paris Observatory.
Oh, is that what it is?
Yes.
Right, okay.
That's why
Right.
the circumference of the Earth is 40 million meters. Which is, and make that kilometers. It's 40,000 kilometers.
Right, so
is the
it
circumference.
comes from-
That's why it's that even.
Yeah.
It's the French did that, but
So
you're
they're all
Brits, so you don't
arbitrary.
care what they did.
Yeah, so they're all arbitrary things that are to do
Yeah.
with our planet or our bodies or whatever it
Yeah,
is.
yeah.
But then you could say, well, but the speed of light, Planck's constant, and the strength of gravity, everyone would agree on.
Even aliens.
So
yes.
yeah, because you
Yeah.
can measure those. So whatever units you measure them in, you can put them together to make something that looks like a length. And
Gotcha.
that's the Planck length. And it happens to be very, very tiny relative to us.
Right.
Very cool.
So can there be a fabric of space-time that, in other words, if you were to quantize general relativity, you would have to, the Planck length would be fundamental to that. Is that not right?
Yeah. So we
Yeah.
think that's telling us something deep about the universe itself.
Okay.
So these are properties of the universe, these things. That's the thing. Not properties of planets or
Right.
people.
Right. Exactly. All right.
Very, very cool.
All
Okay.
right, time for two, maybe one more. All right. What do you got?
All right, this is Big Stu. And Big Stu says, hey, what it do? My name is Big Stu from Austin, Texas.
All right.
I've heard Dr. Cox talk about how information that falls into a black hole might not actually be lost. But what is that information exactly? Does Hawking radiation somehow contain the same atoms that went in? Or does the universe just eject some cosmic thumb drive full of data? I'm trying to wrap my head around this, man. Help me.
Cosmic thumb drive full of data, yes.
Yeah.
So the idea is that the Hawking radiation ends up, yes, the description that who was asked the question?
Stu.
That Stu said is basically right. So in more technical terms, you end up with this Hawking radiation. You'd have to collect it and do some operations on it with a quantum computer to kind of extract the information. So it's all, no one's ever going to do it. It's impossible to do in practice. But that's the idea. In a very fundamental sense, it's in there. In the same way that I suppose the information, if you were to, I suppose, ask the question, how is the information from this photograph I took with my phone encoded in the memory of the phone? It's quite complicated, actually, and it's got error correction in it and all sorts of things like that. And it's that idea, really, but at a quantum mechanical level. So,
Cool.
yeah. So it's not physically
Right.
the physical stuff, but it's the data.
Cool. Very cool.
Time for one more.
All right, this is Wayne Rasmussen, and Wayne says, hello, star nerds.
Nerds unite.
Yes.
Nerds of the world.
Does Newton's third law hold true in quantum mechanics? Wayne from Northridge, California.
To every action, there is an equal and opposite reaction. Yeah.
That was simple. Good enough for me.
I mean,
Yeah, I
so
can't think
let
of any
me
reason
broaden
why
that.
not.
Allow me to broaden it. So quantum physics and relativity has shown that the applicability of Newton's laws has limits. F is not always ma in that simple form. You need Einsteinian extensions on these constructs.
Yeah.
So even with his gravity equation, you have to modify it. And it was hard-earned to learn that Newton's laws fail. So does every action is an equal and opposite reaction have a point of failure where we need a deeper understanding or an updated understanding of how the universe works?
No. So for example, it's easier to explain the first law, everything continues in its state of rest or uniform motion in a straight line unless acted upon by a force. That is to do with the symmetries of space-time, right? So that is true in relativity as well. So if you're talking about special relativity, and it's one of the examples we teach actually in our first year undergraduate course, you can show that if something's traveling in a straight line in one frame of reference, it's traveling in a straight line in a different frame of reference, under both Galilean transformations, which are the Newtonian picture, and Lorentz transformations, which are the special relativistic picture.
Both of them. Okay. Very good.
So you could actually phrase that as one of Einstein's postulates, because Einstein's two postulates from which special relativity emerges are the speed of light's a constant for all observers, and the laws of nature take the same form in all inertial frames of reference. Newton's law that says that something's going in a straight line, unless acted upon by a force, it'll still carry on going in a straight line, is one of those laws. I mean, if you think about the consequences, otherwise you'd be able to change between different points of view moving at the same speed relative to each other. And something that was going along in a straight line, according to one person, would be doing that. Would be in orbit or something. That
we're intact
built
there.
in. So they're a representation of the, ultimately of the, and there's a very deep question as to why is that the case? And I remember again Feynman, who we mentioned earlier, talking about it. Why is that the case? And he said it's because it's one of the fundamental properties of our universe. So we don't know why that's the case.
It just is.
That is the way our universe is built. It's to do with the posh way or whatever the fancy way of saying it is the symmetries of space-time. But it's just, that's one of the fundamental properties of our universe.
I'm going to end with something completely irrelevant.
Okay.
But he mentioned the Galilean transformation.
Yes.
There's a game played by the Seattle Seahawks.
Correct.
And I'm in email
with Pete Carroll.
With Pete Carroll, okay? So I'm on his radar, he's on my radar, and their quarterback did a lateral on the field that was being challenged by the opposing side.
I say illegal forward pass.
Illegal forward pass. He's already passed the line of scrimmage, and he's going to his running back, tosses it to the running back catches it, and they get a first down, and they would ultimately score. And he said to me, Neil, I think what we did was legit. What can you help me here? And I looked at it, and so I posted online that it was a legitimate Galilean transformation. So here's what's happening. He and his running back are running down the field. He is ahead of his running back. He pitches to his running back. He's ahead of his running back when he let go of the ball. He's ahead of the running back when the running back caught it.
Right.
Okay?
And he lets go of the ball before the line of scrimmage.
No, it's after the line of scrimmage.
No, that would be an illegal forward pass.
I'm getting, no.
No, he has to let go of the ball before the line of scrimmage.
No.
The receiver caught it after the line of scrimmage.
No.
That's the only way this can work.
No.
Okay,
Hear me out.
let me hear you.
Please.
Go ahead.
Please. They both are well past the line of scrimmage. Both of them. He's ahead of his receiver, pitches it backwards to him.
Oh, you mean they're running together?
Yes.
Oh, that's a different story. Go ahead.
Pitches it back to his running back.
Right.
Okay? The whole time he's in front of him.
That's correct.
But they're running so fast that from the reference frame of the gridiron, the ball actually went forward.
No, that makes sense.
Okay.
Yes.
So I said, this is a Galilean transformation. You cannot penalize football players for running fast. Okay.
Right.
You can't do that.
Should have been 2 white players.
Stop. He's in race therapy. He's getting out of it. He's gotten much better, by the way.
Funny. That was funny.
It was 2 black players, by the way.
They're fast. What can we say? Okay, go ahead.
So it turns out that they let the call stay that it was a legitimate lateral. Even though, according to the field, it was a forward pass.
No, it would have looked like if you're running fast, that's what it would look like.
Yeah, and so that was a Galilean transformation where whatever else is happening, your reference frame is moving and everything is happening in that moving reference frame.
Very cool.
Galilean transformation.
Awesome.
Yep. Yeah.
Science.
You know how we did it on a explainer once. Have you ever been on the highway and then these cars racing each other around you?
Oh yeah, that was.
It feels really dangerous.
Right.
But in fact, as far as they're concerned, you're just standing still.
Right.
And they're just darting around you.
Yeah.
And so they're in their own reference frame, and you're just blockage.
Yeah. So there's
we're all going 40 miles an hour in slow traffic, and they're going 70 miles an hour around us.
Right.
And it's less dangerous than it looks, is all I'm saying.
But don't do it, Pete. Okay? Follow the laws of the road.
Brian.
And buckle up.
Delight to have you visit
Always a
our
pleasure.
humble city, my humble office. Don't be such a stranger. But you're a busy guy, so we allow this.
Yeah.
Oh, okay.
And we'll look forward to your Emergence tour. I assume it's another international booked tour.
Yeah, it comes to the US, and I think the tickets are on sale for the end of next year and the start of 27.
Damn, the boy's got his calendar.
He's already.
But the New York date, the East Coast dates are not yet on sale actually, but they will be.
Okay.
Okay.
You going to come back to the Beacon Theater, which is where I last saw you?
I think so.
No,
I
he's going to
think.
say, I'm coming to
We're
Yankee
moving
Stadium.
up. Yeah.
Giant
We're moving up.
stadium.
It's Madison Square Garden this time,
But
buddy.
we did the town hall as well,
Town
which
Hall's
was
a good
Town Hall's a nice-
I love that.
great
We
venue.
did-
It's a little more
so-
intimate. Yeah.
I'm not sure which one.
Okay, Town Hall's a venue in New York City.
Yeah.
It's called Town Hall.
Yeah.
They're both great venues,
They're both
though.
great venues. All right, this has been a delightful, I think long overdue episode with my friend and colleague and partner in crime, trying to educate the world of everything cool in the universe and especially in the world of particle physics, Brian Cox. Thank you, Brian.
Thank you.
All right. And Chuck, always good to have you, man.
Always a pleasure.
I'm Neil deGrasse Tyson, your personal astrophysicist. As always, I bid you to keep looking up.